Hi, and welcome to Physics 2212 Lab 4. Introduction and purpose of this lab was to predict behavior of circuits regarding resistors and capacitors. Preview experimental results matched ones predicted from formulas, and current in RC circuits is time dependent. The fundamentals and models of this experiment were the node rule, the loop rule, and the Ohm's law, which is shown here. This is the loop rule, node rule, and Ohm's law. Assumptions that we made were that resistance of wires and ammeter is negligible to simplify calculations. This would not be true in a real world situation, but it's an assumption we made to simplify what we're actually calculating in this experiment. So for the experiment, the system, I chose the circuit, and surroundings I chose as everything else. The initial conditions and model were that testing different combinations of resistors and capacitors using the PhET simulation. Our prediction is that I1 is equal to I2, which is equal to 0.02 ammeters, and two 1.5 volt batteries, 2 ammeters, 47 ohm resistor, 100 ohm resistor. Math is that RAF is equal to 47 plus 100 ohms, which is equal to 147 ohms, which leads to V over R is equal to 0.02A. Current is negative 0.02A when ammeter is backwards, just because you flip the sign. Replace this with volume meter. V is equal to 1.5 plus 1.5 is equal to 3 volts, and I is equal to 0 because it's an open circuit and no current will flow. Here are the potential differences. B minus A is 3 volts, C minus B 0, D minus C negative 0.96, E minus D is 0, GF 0, HG 0, AB 0, and F minus E is negative 2.04. Net dV is going to be 0, and current doesn't flow through the volume meter due to its high resistance, which means the current stays the same. And here are the charts along with the points at which we took the calculations for potential differences. For the experiment, what happens to the current when the volume meter is replaced with with an ammeter in parallel with 100 resistors? It'll increase to 0.06 because the current is split at the node, so only a portion of the current experiences the resistance. And our new resistances would be 48 ohms, 1 to 2 ohms, 0 ohms for the wire, and 0 ohms with ammeter. Part 2 of the experiment, the initial conditions, 2 bulbs with R is equal to 10 ohms, 20 ohms, 1 9-volt battery, and a 200 MF capacitor, sorry. Battery was the 10 ohm bulb, or there's a battery, 10 ohm bulb, and capacitor. Light brightens quickly and then it'll die. The capacitor charges as current decreases to 0. For the 20 ohm bulb and capacitor, light brightens quickly and then dies, and the capacitor will also charge as current decreases to 0. The 10 ohm bulb took 10 seconds to charge, 12 seconds to discharge, and the 20 ohm bulb took 15 seconds to charge and 22 seconds to discharge. The RC circuit, the circuit was a 9-volt battery, 200 MF calculator, 300 ohm bulb. Process was the capacitor's discharge, voltage, and time are recorded, plotted, and linearized using these two formulas. Discussion. So our expectations were that the experiment results matched ones predicted from formulas. The current in RC circuits is time dependent, and this was observed to be true when we assume, zero resistance for ideal conditions, although this isn't always true in a real life scenario. So some errors that could have occurred was a human error with the stopwatch, which would have skewed the results and caused inaccurate voltage measurements. Other human errors could include calculation errors, and other errors in overall experiment. Most of the error would be eliminated by the ideal simulation, but this wouldn't always happen in a real life scenario. So questions: what if we were to do this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What difference about a real ammeter, and how would it have affected the circuits you hooked it up to? The ammeter would have had actual resistance instead of none, so the current would decrease overall over time. And what if you were doing this lab in real life and used a real battery to charge the real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? With no resistance, the capacitor would reach full charge immediately, but this would never happen in real life since the capacitor contains a slight resistance, which will slow the process down. Thank you.